In this lesson, we are going to take a look at special right triangles. And there has been some feedback to me that people like the videos I do when I do them on paper. And so I will try to switch back and forth, especially if there's something I feel like has a pretty complex construction on it. This one actually doesn't have any constructions, but there is going to be an algebraic concept about simplifying radicals. I'm going to walk you through that a little bit, but I'm also going to put another video link in the chapter 410 links, where if you want more information about how to simplify radicals or just want a bit of an in-depth lesson, I will link to that as well. So let's take a look at our warm-up here. We have right triangle ABC and has a leg of length 15 and a hypotenuse that's 9 root 3. How long is the other leg? So if I'm just going to sketch this out for a second, one of the legs is 15, the hypotenuse is 9 root 3, and we don't know what the other leg is. So of course, to figure out the missing leg, we are going to apply our Pythagorean theorem, which is a squared plus b squared equals c squared. Again, a and b interchangeable because the legs, it doesn't really matter which one's which. So we'll do 15 squared plus b squared. And this is important. When we do 9 root 3 squared, we have to put it in parentheses. And I'm going to go over here. You can certainly use your calculator. But when I do 9 root 3 squared, I'm going to do 9 root 3 times 9 root 3. And this is where I mean, if you need some more in-depth radical rule, just coaching or just to kind of really make sure you understand it. So 9 times 9 is 81. Remember, this is all multiplication, so it's commutative. And then when we take root 3 times itself, one of our radical rules says if we have the same index, right? So this is a square root, this is a square root. We can just multiply what's underneath the radicands. That's what those are called. And so we do 3 times 3 is 9. And so then the root of 9 is 3. And that's the same thing as taking the square root of 3 and squaring it. And since squaring and square rooting are inverses, that's also another justification for why we get 3 here. And then 81 times 3 is 243. Just remember, your calculator will do this for you, but when you push it in your calculator, you have to use the parentheses. If you don't, it will just square the root of 3, and then it will multiply that answer by 9, and you'll end up with 27 and not 243, which you should end up with. 15 squared is 225. And then, oh, that does not look like a good 243. And then we're going to go ahead and subtract 225 from both sides. And then b squared is 18. And now when we take the square root of both sides, b is root 18 centimeters, which if we wanted to simplify this, and this is like really the part of the radical rules that you need to know, what we would want to do is we want to ask ourselves, are there any perfect squares that go into the square root of 18? And the answer is yes, it's 9. So we can break this apart. So the square root of 18 is the same thing as saying the square root of 2 times the square root of 9, because 2 times 9 is 18. And since the square root of 9 is 3, this is the same thing as saying 3 times the square root of 2. And if you punch this in your calculator, if you punch in the square root of 18, and get a decimal, and then you also punch in 3 times the square root of 2 to get the decimal, you will notice those are the same decimal value. I don't really mind if you leave your answer as the root of 18, but we do need to simplify radicals in this lesson today to find a pattern. So that's why I'm kind of making a big deal about it. Usually, or sometimes we also do in a decimal approximation, but a lot of times we leave it exact. And that's also going to be something that we focus on as we move throughout geometry. When are we going to leave our answer exact, and what exactly does that mean to leave our answer exact? We are going to investigate two types of special right triangles today. The first one is an isosceles right triangle. So when a right triangle is isosceles, the two legs are going to be congruent. We always know the hypotenuse is the longest side. It's across from the largest angle. And the only way to have then an isosceles right triangle is if the legs are congruent. So I'm going to complete a couple steps of this table, and then we're going to see if we can generalize it. So if I have a right triangle where the legs are both 1, and I want to find the length of the hypotenuse, I'm going to do 1 squared plus 1 squared equals, and I'm going to just call it h squared, or I could call it c squared. So 1 squared is 1, 1 squared is 1, and h squared, and 1 plus 1 is 2. And when I take the square root of both sides, there's nothing I can do with 2, taking the root of that. So my hypotenuse is the square root of 2. Let's try that again. What if my legs are length 2? So now I'm going to do 2 squared plus 2 squared is h squared. Remember that I square first. So 2 squared is 4. 2 squared is 4. 4 plus 4 is 8. Now this is where we want to simplify our radical. If I leave this as the square root of 8 and I plug that in here, I'm not going to see any pattern. So I can think of 8 as the square root of 4 times the square root of 2, because one of my rules is if I have a square root, I can break it down into a product. Kind of like I'm thinking about a factor tree. But when I do that, I want to make sure I'm breaking it down into things that are perfect squares. So the biggest perfect square that goes into 8 is 4. But then the square root of 4 is 2. So then I can rewrite this as 2 root 2. Or 2 times the square root of 2. So again, when my leg is size 2, my hypotenuse is size 2 times the root of 2, or 2 root 2. Let's do one more. Let's do 5, just to kind of mix it up a little bit. So 5 squared plus 5 squared is h squared. Again, I'm going to use my Pythagorean theorem, square it, and then add. And then taking the square root of both sides, to break up the square root of 50, it's the square root of 25 times 2. And so that simplifies to 5 root 2. Are we noticing a pattern? Hopefully we are. If you feel like you need to do more, please do that. But what's going to happen is, if my leg is 3, my hypotenuse is 3 root 2. If the leg is 4, my hypotenuse is 4 root 2. Going down the line, so if my leg is L, my hypotenuse is L root 2. And we're going to prove that in a second. So this is my isosceles right triangle conjecture. In an isosceles right triangle, if the legs have length L, then the hypotenuse has length L root 2. So this is kind of nice. If we have a special right triangle, or an isosceles right triangle, we don't actually have to use the Pythagorean theorem anymore to get these other side lengths. All we have to do is apply this shortcut. And again, this is inductive reasoning, right? We're taking specific examples and we're getting something general. And this just makes our life a little bit easier. It's not that we can't apply the Pythagorean theorem. It's just anytime we can get something even more efficient, we always try to do that as mathematicians. So let's take a look at these examples. For this first example, we're trying to find A, and A is the length of the hypotenuse. Again, we can see that it's across from the right angle. So if my legs are 14, then my hypotenuse is 14 root 2. All I have to do is multiply that leg by the root of 2 to get the hypotenuse. Number 2 is a little bit different. In this case, they're giving me the hypotenuse, which is 12. And so the question is now, what is the length of the leg? Here's what I like to do here. I like to set up an equation. So I know that my hypotenuse is my side length times the root of 2. That's something that I discovered. And now I'm going to substitute 12 in for that length of the hypotenuse. And my goal is to solve for L because that's the leg length. Well, to do that, I would do an inverse operation, which is to divide. And I'm going to leave this as 12 over the root of 2 centimeters. There is a way to what's called rationalize the denominator when you're working with radicals and you don't want a radical in the denominator. The reason why we call it rationalizing is the square root of a non-perfect square is called as an irrational number. And so right now we have an irrational number in the denominator. And when we rationalize the denominator, we then get something that's rational. So usually it's an integer, but it could be technically a decimal that's, terminating or something. That is a little bit beyond the scope of our course, just in terms of it's just algebra that I don't necessarily think we need to dive into right now. So it's okay if we leave this 12 over the root of 2. This one has a label as centimeters. This one doesn't. I do usually just say, let's use centimeters. So for the last part of this video, we are going to prove the isosceles right triangle conjecture and just do a quick paragraph proof. All right, so again, we're proving the isosceles right triangle conjecture. So we want to show that the hypotenuse of a right triangle is L times the root of 2. That's essentially what we're trying to show. So we're going to say, given an isosceles right triangle with legs length L and hypotenuse length H. So that's our setup. Well, what did we use in the investigation? The Pythagorean theorem, right? By the Pythagorean theorem, L squared plus L squared is H squared. Then what we're going to do is we're going to combining like terms. Combining like terms. So these are like terms because they both have the same variable parts. So we have 1L squared plus 1L squared. So we get 2L squareds is H squared. And then taking the square root of both sides. I'm sort of running out of room here, so I'm going to kind of go over here. 2L squared is, so the square root of 2L squared equals the square root of H squared. And then I'm just going to use one of my arrows, and that's going to give me L here because the square root of L squared is L. But the 2 has to stay under the radical. And then I can take the square root of H squared, which gives me H. And that's what I wanted to show. So great job looking at the isosceles right triangle conjecture.